Welcome to the deep dive. Today we're venturing into the really fascinating world of meandering rivers.
Yeah, rivers that curve and bend.
Exactly. But we're not just looking at the curves themselves. We're digging into what happens when these, natural wanderers kind of hit a wall, geologically speaking.
Right. It's like watching a river try to do its thing, but the landscape itself is pushing back, restricting its movement.
And we've got a guide for this exploration, a research paper.
We do. It's titled A Model-Based Characterization of Confined Meandering Rivers. Really insightful stuff.
Okay, so our mission today is basically to unpack how this confinement shapes these rivers, right, using this paper.
Precisely. To understand the mechanics, the patterns, and pull out the key insights from the research.
Now, I know meandering rivers and encountering geological boundaries might sound, well, a bit technical, maybe dry.
It can sound that way.
But honestly, stick with us, because there are some genuinely surprising facts and kind of mind-bending ideas in here.
Absolutely. It gets really interesting when you look closely. So I think the best place to start is the fundamental difference, right? Free versus confined.
Yeah, let's set the stage. So when you picture a classic meandering river, you probably imagine it, snaking way back and forth across a big, wide, flat floodplain.
Mm-hmm. Lots of room.
That's your classic unconfined river, a free meanderer. It's got space to roam, create those big sweeping loops over time. It's wandering through terrain that's pretty much the same everywhere.
Exactly. Relatively homogeneous stuff. Easy to erode. But then you get these confined meandering rivers.
The ones that are squeezed.
Yeah, the ones forced into valleys or areas where the rock underneath is just tougher, less erodible. Figure 1 in the paper, it shows this really well.
What does it show?
You see these almost like squared off bends where the river is really hemmed in. Quadrangular bends, they call them.
Wow, blocky.
And then long stretches where the river is just stuck right up against the valley side. Even where the confinement isn't super strong, you see these sort of stretched out, elongated bends. They just behave differently.
So these harder boundaries, they really mess with the river's natural tendency to wander and curve. It makes sense the shapes would be different. But the paper points out a big problem was, how do you actually measure how confined a river is?
That's been a real challenge, yeah. How do you quantify squeezed? It's a bit subjective just looking at it.
So what did the paper do?
Well, this is key. They introduced a concept called the confinement ratio, CR for short.
Okay, CR sounds important. What is it measuring?
It's actually pretty straightforward conceptually. It's the ratio of the valley width. They call it WCV tress.
Okay, how wide the valley is.
Right. To the width the meander belt would have if there was no confinement at all. That hypothetical width is WMB.
Ah, so it's comparing the actual space the river has to the space it would use if it could roam free.
Precisely. Figure 2 illustrates this. You see the valley, WCV, and then this wider potential area, WMB. So CR basically tells you how much the geology is dictating the river's path.
So low CR means tight confinement.
Exactly. Narrow valley compared to the potential width. And a high CR, like above 1, means it's getting closer to being unconfined. Lots of room.
Got it. But how do they figure out that hypothetical width, the WMB, the width it wants to be?
Good question. It's not something you can just measure directly, obviously. So they mentioned 2 main ways. One is numerical modeling.
Running simulations.
Yeah, simulating how the river would evolve without those valley walls. The other way is using a simplified empirical relationship, basically a formula.
Ah, okay. They even give the equations, I see. WMB equals 3.4 times lambda hat star.
Yeah.
Sounds a bit complex.
It gets a bit mathy, yeah. Lambda hat star itself depends on channel width and friction, but the main point is they have ways to estimate that unconfined width.
And do these methods agree? The simulation versus the formula?
Not perfectly, actually. They note that the numerical method tends to give WMB values about 30% higher than the simpler equation.
Interesting. Shows it's not quite an exact science.
Definitely highlights the complexities involved in modeling these natural systems.
Okay, so we have this CR, this confinement ratio. How does it help us analyze these confined rivers better? What other tools did the paper introduce?
Well, they still use the standard metrics, things like sinuosity, how wiggly the river is overall.
Sigma.
Yeah, sigma. And local curvature, see how sharp the bends are, and half meander lengths, LH. But they also developed 2 new metrics specifically for confined rivers.
Ooh, okay. New tools. What are they?
The first one is the boundary approaching index, BA index.
Boundary approaching. Sounds descriptive.
It is. It measures the percentage of the river's total length that gets really close to the valley boundaries,
How close is close?
within about 3 times the river channel's width from either side. Figure 3A shows this.
And what do they find? Does it relate to CR?
Strongly. As you'd expect, for low CR values, strong confinement, the BA index is really high. The river spends a lot of time hugging the walls.
Yeah, nowhere else to go.
Pretty much. And interestingly, when the confinement is really tight, other factors like the channel's own shape, its width to depth ratio, which they call the aspect ratio, beta, that becomes less important.
Right. If the walls are squeezing it, the channel shape itself doesn't matter as much for how often it hits the boundary. Makes intuitive sense.
Yeah.
What's the second new metric?
That one's called the River Valley Intersections Index, RVI.
RVI.
Okay, what's that come?
Imagine drawing a grid of evenly spaced lines across the valley perpendicular to the valley's main direction. The RVI counts how many times the river's center line crosses these lines.
Ah, okay, so it's measuring how much the river kind of zigzags or wanders back and forth within the valley?
Exactly. It quantifies that degree of wandering within the confinement.
Yeah.
Figure 3B helps visualize it.
And how does RVI relate to confinement? They found that, on average, RVI tends to decrease as CR increases. So more space, less forced crossing back and forth.
Less zigzagging when there's more room.
Right. But they also noted that something called the river's morphodynamic regime can influence this RVI index too.
Okay, let's pause there. Aspect ratio. Can you just quickly define that again in river terms?
Sure. Aspect ratio, beta here, it's the ratio of the river's width to its depth. So is it wide and shallow, or is it narrow and deep? That's the basic idea.
Got it. Width to depth.
Yeah.
And morphodynamic regime. Sounds complicated.
It relates to the river's sort of internal dynamics, how its bends naturally tend to grow, migrate, and skew over time based on flow and sediment transport. Think of it as whether the bends tend to move upstream or downstream, and whether they lean towards the upstream or downstream direction.
Okay, so it's about the river's own personality of meandering, separate from the valley walls.
Kind of, yeah. Though obviously the confinement interacts with that internal tendency.
This is giving us a much more detailed picture. But these metrics describe the shape. What about the processes? How these rivers change over time? Did the paper model that?
Oh, yes. That was a big part of it. They ran 40 long-term numerical simulations.
40? Wow.
Yeah, varying the confinement ratio, CR, and that aspect ratio, beta. And the really cool thing, the simulations produced planforms, map views of the rivers that looked remarkably like real confined rivers.
But they compared them to actual satellite images.
They did. Figure 5 shows some simulation results next to images of rivers like the Beaver River in Canada. The resemblance is quite striking. Quadrangular bends, reaches stuck to the valley wall. It all shows up in the model.
That's fantastic validation. So the model captures the look. What did it tell them about, say, sinuosity under different CR levels?
Okay, figure 6 has the results. It shows that average sinuosity tends to be lower when confinement is strong, low CR, and the sinuosity also fluctuates less over time in those tight conditions.
So less wiggly overall and more consistently less wiggly.
Exactly. They saw distinct behaviors below CR of about 0.1 and above a CR of 1. And importantly, the model's sinuosity values matched up pretty well, generally, with measurements from some actual confined rivers they studied.
So tighter squeeze, less wiggle. Seems logical. What about the size of the wiggles, the meander length?
Figure 7A covers that. Weak or no confinement allows for longer wavelengths, bigger loops. Strong confinement tends to result in shorter, more compressed meanders. There's a transition zone in that moderate confinement range.
And the sharpness of the bends, the curvature.
That increases significantly under strong confinement, CR less than 0.1. You see that in Figure 7B. The river is forced into tighter turns more often.
And that boundary approaching index, the BA. Did the simulations confirm rivers stick to the walls?
They did. Over the long-term simulations, rivers in low CR scenarios spent a large percentage of their time right up against those boundaries. Figure 8 shows this clearly with box plots. It confirms observations from earlier studies, too.
Okay, but rivers aren't static. They move, right? They migrate. And they cut off loops, forming oxbow lakes. How does confinement affect that dynamism?
This was really interesting. Figure 11 looked at the migration rate, how fast the channel moves sideways. And surprisingly, the average rate didn't seem to change all that much across different confinement ratios.
Wait, really? Even when it's super confined?
Yeah. The interpretation is that while lateral migration is restricted, strongly confined rivers might actually compensate by migrating more longitudinally along the valley axis.
Huh. Trading sideways movement for downstream movement, perhaps? That is unexpected. What about the Oxbow Lakes, those cut-off meanders?
Fewer of them in strong confinement. Figure 12 shows this. The simulations produced fewer abandoned meanders when CR was low.
Makes sense. If you can't swing wide, you can't easily cut off the loop.
Exactly. Figure 12 shows the total length of these abandoned meanders is lower at low CR, which kind of mirrors the sinuosity trend. Less wiggly, fewer cutoffs.
But you mentioned the real-world data was slightly different there.
Yeah, there was a slight contrast. The data from actual rivers they looked at suggested maybe a slight increase in the relative length of abandoned meanders with CR. It hints that, real-world processes might have extra complexities the model doesn't fully capture yet, maybe different cutoff mechanisms.
Speaking of cutoffs, didn't the paper mention different types of cutoffs in confined settings?
Yes, figure 13 is cool. In the simulations under strong confinement, they saw two main types of neck cutoffs, where the narrow neck of land between loops gets breached.
Okay, what were they?
Type 1 involved two consecutive, sort of skewed loops basically merging together. Type 2 happened when a smaller, secondary loop formed within an already constrained bend and then got cut off, and they found real-world examples that looked qualitatively similar to both types.
So the model is even giving clues about how these confined rivers change shape, this specific mechanism.
Right, it's not just about the static form, but the processes too.
Let's dig into the physics a bit. Why do confined rivers stick to the walls so much? What's the mechanism?
Well, the paper links it back to point bars. Those are the sandy deposits on the inside of meander bends.
Right, they build up as the river erodes the outer bank.
Exactly. In unconfined rivers, point bars grow and help the meander migrate smoothly. But when a river is pressed against a valley wall, there's just less room for those point bars to develop properly on the confined side.
Ah, so the lack of point bar growth kind of pins the river there.
It limits the river's ability to curve away from the wall. The boundary imposes a curvature limit. But they also mention something called morphodynamic influence.
What's that?
Even when a reach is stuck against the wall, changes happening in the bend upstream, like how the flow is directed, can still exert some force, some influence, potentially trying to push the river away from that constraint over very long time scales. It's a subtle effect.
And you mentioned those subresonant and superresonant regimes earlier. How does confinement interact with those internal river tendencies?
It's a bit theoretical, but the idea is that a river has a natural way it wants to migrate, maybe upstream with downstream skewing, superresonant, or downstream with upstream skewing, subresonant.
Okay.
Confinement can obviously override this. If the walls are tight enough, the river does what the walls dictate. But the paper suggests that, especially in moderate confinement, this underlying regime might still influence the style of meandering, even if the overall pattern is constrained. Though they admit at very strong confinement, low CR, the walls pretty much dominate everything.
It's like the valley geology is the loud music drowning out the river's preferred rhythm when things get tight.
That's a good analogy, yeah.
Okay, so putting this all together, the research seems to offer a way to actually classify these rivers based on how confined they are.
It does. Based on how all these metrics, sinuosity, curvature, meander length, abandoned paths behave as you change the confinement ratio, CR, they propose three main categories. Figure 14 summarizes this.
Let's hear them. What are the classes?
First, strongly confined. This is where crya is less than about 0.1.
Really squeezed.
Really squeezed. And in this zone, things like sinuosity and curvature don't really change much more if you make it even tighter. They're already maxed out, or rather minimized, by the confinement. The channel shape, beta, also has less impact here.
Okay, strongly confined, CR 0.1. What's next?
Moderately confined. This is roughly between CR 0.1 and 1. In this range, all those parameters we talked about are very sensitive to the exact value of CR. Small changes in confinement can lead to noticeable changes in river shape and behavior.
In transition zone.
Exactly. And finally, unconfined, where CR is greater than 1. Here, the valley walls are far enough apart that they don't really restrict the meandering much. The river's characteristics, like sinuosity, tend to reach stable values that depend more on the river's own properties.
Right.
Its aspect ratio data, rather than the confinement.
Strongly, moderately, and unconfined, based on CR. That's a neat framework.
It is, and they connect it back to earlier work, showing it aligns reasonably well with classifications proposed back in the 70s, which is always nice to see that consistency.
Definitely. Now, we should also touch on the limitations, right? No study is perfect.
Absolutely crucial. The authors are upfront about this. One big one is the lack of extensive long-term field data to really rigorously test the model, especially in that moderate confinement zone.
Real-world data is hard to come by on those timescales.
Very. Also, they mostly relied on interpreting confinement from satellite images, which involves some judgment. Ideally, you'd have detailed geological data about erodibility everywhere.
Makes sense.
What else? The model itself has simplifications. It uses basically just two levels of erodibility, floodplain and bedrock. Real landscapes are more complex,
Yeah.
and they used idealized straight valley walls. Plus, that simplified formula for estimating the unconfined width, WMB, has its own uncertainties. And the underlying math of the model has limitations for very, very sharp bends.
Okay. And did they look at rivers stuck only on one side?
No, they mentioned that specifically situations where a river might be up against a cliff on one side but have a wider floodplain on the other. That wasn't covered in this particular study.
So plenty of avenues for more research.
Definitely. But even with those limitations, this work provides a really valuable quantitative framework.
Yeah, it feels like a big step forward. What are the main takeaways for you?
I think the big ones are the confinement ratio, CR, is a genuinely useful metric for understanding and classifying these rivers. Those two new indices, BA and RVI, give us quantitative ways to describe planform shapes shaped by confinement. And the model successfully identifying those three distinct regimes, strongly, moderately, unconfined, and showing how river behavior changes across them. That's pretty powerful.
It really highlights how geology fundamentally controls these dynamic systems. It's not just water flowing, it's water interacting constantly with the earth it flows through.
Exactly.
So here's a thought for you, the listener. Think about a river, maybe one near you. Look at its valley. Is it wide open, or is it flowing through a narrower valley, maybe even a gorge?
Yeah, try to picture it.
Based on what we've talked about, would you guess it's strongly confined, moderately confined, or basically unconfined? What clues in the river's shape, tight bends, straight reaches against a valley wall, or wide sweeping loops might back up your guess?
It's a great way to apply these ideas. And if you want to go deeper, absolutely check out the paper or just spend some time on Google Earth or other satellite imagery exploring different rivers with this idea of confinement in mind. See if you can spot the patterns.
You really can start to see the landscape differently.
You can.
Well, thanks for joining us on this deep dive into the sometimes constrained but always fascinating world of meandering rivers.
My pleasure. It's a great topic.
Until our next exploration.